So we continue talking about the second law of thermodynamics. You can see it's so riveting that Lucy is just completely passed out. Izzy has left us. If you're watching lecture 18 with us, yeah, Izzy said this is too boring for her. She's gone. But Lucy, as you can tell, is hanging on not well, but she seems very comfortable. I don't know. Maybe we'll lay down, take a nap here in a little bit. Doesn't sound like a bad idea. Let's continue on, shall we? Let's talk about so in lectures 8, I'm sorry, 19 and 20. We got lectures 19 and 20. And these are just going to be example problem after example problem, looking at Gibbs equation applied to multiple different ways. Okay, so using the second law for water in R134, we're going to use property tables for S values, but we've just derived Gibbs equation at the end of lecture 18. We're going to apply Gibbs equation to figure out the change in entropy values for substances that the property tables don't really give us that information. So, one of those cases when we talked about solids and liquids. If I've got a solid staying a solid or a liquid staying a liquid, these are situations that I can use Gibbs equation to determine what the entropy change is, right? So most of you have done this with me before. You know how this is going to go. You see the whole problem there. I'm going to write down the givens, and then we'll switch to the document camera, um, and we'll go from there. So what do we got here? We've got this insulated tank. So I'm going to put some shading around it to represent insulation. So we got this insulated tank sealed up. And inside this tank, we've got water and we got a hunk of copper. All right, so we got water and copper. And again, I'm gonna go full screen with this so if you don't see exactly what I'm writing, that's okay. I'm just labeling things. What do we know? We know the volume of the water, which I'm just going to subscript as W. VW is 120 liters. We know the mass of the copper, MCU, so I'm going to subscript CU for copper, 50 kilograms, big chunk of copper, about 100 pounds or so, for those of us that think in English units. The initial temperature for the copper is 80 degrees C, so it's pretty warm, right? You wouldn't want to try to hold that in your hand. Not everybody thinks in Celsius. Those of us who have grown up in the States, we don't think in Celsius, so it's a bit foreign to us. That is hot. Initial temperature water, kind of room temperature water, 25 degrees C, maybe a little chillier. What are we looking for? We want to find the final temperature, and we want to find the entropy change, delta S. Okay. All right. So the problem statement wouldn't just look like this. It'd say that a chunk of a large mass of copper is placed in a insulated tank with water at 25 degrees C. If the copper is initially at 80 degrees C with a mass of 50 kilograms, determine the final temperature in the water bath of 120 liters and also the entropy change for the process. That's the problem statement would say something along those lines. So here we are. Those of you who have been with me for a while now, you know, first question I'm going to ask is, okay, where do we start, or how can we find this final temperature, right? Maybe we call it, I don't know, call it T2 something or other. And I'll wait, you know, what are some tools? What's the way we go about it, maybe? Just at a gag reflex, a lot of people will say, well, what about the first law? Okay, well, let's look at the first law. First law says draw your system. Well, if this is our system, and again, it said it's insulated, so there's no heat transfer. What crosses the boundary? Well, if this is my system boundary, what crosses the boundary? When you write the first law equation, the entire left-hand side is zero. There's nothing crossing the boundary. The only thing going on is you've got a change in internal energy. Now, what's different for us is now I've got two different components inside this system where I'm used to just one, and you could treat the copper as one system and the water as another, and one's losing heat to the other, kind of like we might in the heat exchanger. But there's no reason to do that. We could just say, well, it's two pieces of the same system, and they're both going to undergo internal energy changes. You're going to have an internal energy change for the copper, and you're going to have an internal energy change for the water. Now, how do we find those? Well, I've got liquid water at 25 degrees C, and the hottest the water is going to get to is 80 degrees C. Unless this water is at basically on the surface of the moon, essentially a vacuum, we're not dealing with a vapor here. This is going to be liquid water at these temperatures. So the water is going to be liquid staying a liquid. And the copper is nowhere near its melting point, and all it's going to do is cool down. So it's solid staying a solid. So I've got solid copper staying solid copper. I've got liquid water staying liquid water. I can treat these as solids and liquids with constant phase. So all that to say, this zero, the energy crossing the boundary, which is zero, is going to equal the mass of the copper times the change in internal energy for the copper plus the mass of the water times the change in internal energy for the water. And what I would do is, given the fact that I know temperature is here and I'm looking for another temperature, maybe I just use um, specific heat, right? In general, I wouldn't use specific heat for water, but this is kind of the one rare case where I could use specific heat for water because I've got liquid water staying liquid. So I'm going to use the specific heat for copper times the temperature change for the copper. And I'm going to use then the mass of the water, the specific heat of the water times the temperature change for the water to describe and use that C sub P times the temperature change to find the internal energy. Now, two questions sometimes come up. Steve, why are you using C sub P for delta U? I thought that was H's. For ideal gases, C sub P is used for H's and C sub V is used for delta U's for ideal gases. These are not ideal gases. So our text, the Chengle and Bowles text, they use C sub P to describe the specific heat of solids and liquids. A lot of texts will just use C. Ours uses C sub P. It's okay. Some might still be struggling with why am I using U values here? It's because it's the stuff that's not flowing. It's inside the system. We only use H's when it's flowing or constant pressure boundary work. But hopefully we're starting to wrestle with that, and that's becoming less of an issue. But if it is, if you're still trying to say, hey, when do I use H's and U's? You really want to get that figured out. Feel free to email me and let's get that figured out with you, okay? All right. So here's what I would ask the class. Okay, what do we know? I've got an equation here. Do I have as many equations as I have unknowns? Well, what do we know? What do we not know? I know the mass of the copper. Okay, mass of the copper is known. I don't know the mass of the water. I do know the volume of the water, and I know it's liquid water, so I most likely can say, well, because it's in the liquid form, the mass of the water is going to equal the volume of the water divided by the density of the water, and that would give me the mass of the water. Okay, I know the initial temperature for both the copper and the water. I can find the mass. I'm going to go look up in property tables the specific heat for the water and the copper. But notice I've got T2 for the copper and I've got T2 for the water. And I always like to ask my class, how can I solve this? Because that's I've got now basically two equations with three unknowns. I don't know the mass of the water, but I've got a clear path to find it. I don't know T2 for the copper and I don't know T2 for the water. Right. And I would pose this to my students. So how do I do that? I got one equation with T2 for copper, T2 for water, both unknown. How do I deal with that? All right, and you can pause it and wrestle this over. But ultimately, the answer I'm looking for is that, well, the goal is to find a final T2 where basically this temperature of the copper equals the temperature of the water. They come to a thermal equilibrium with each other. They reach the same temperature. So it's ultimately what we're after is we want T2 for the copper to equal T2 for the water. That's just one unknown. Okay. So one equation, one unknown here, T2 being the unknown that I'm looking for. Good so far. That's not all the problem asked for. The problem did ask for the entropy change. Problem asked for the entropy change. Okay. Well, let's solve for T2 and then we'll tackle that. So let's actually put numbers to this. Okay. So here I'm going to need to go get properties. Right? Properties. The fact that I've got liquid water, that alone is enough to tell me the density of the water, and this is in metric units, is about 1,000 kilograms per meters cubed. That would be sufficient. It's like 999 something, depending on the temperature. That would get us in the ballpark. It's to three significant figures good. Now, the fact that I've got water and I've got a temperature is going to give me specific heat for the water. Okay, so let's go look at that because I need specific heat. This gets me to the mass. I need specific heat for the water, and I'm also going to need it for the copper. Okay, so if I share screen here, I think I've got property tables open. Yes, I do. This is table A3, part A for liquids. Right, table A3 goes on for a couple of pages. This is A3A. This is the sixth edition of Changle and Bowles. This column is temperature. This column is density. This column is specific heat. So let's go look. Now, notice the temperatures are different. So at 0, it's 1,000. At 25, it's 997. And at 50, it's still 988. So it's okay. And notice the specific heats down here, right? Right. So what is my average temperature? Because basically here I'm using an average temperature C sub P. Well, the thing is I don't know my average temperature. I just know one temperature. So normally this would require a guess and check. We're going to do that with the ideal gas problem. We're not going to do it with the solids and liquids. But normally this would be a guess and check. I would have to guess a T2 to find a T average, get me a C sub P average, calculate a better guess at T2, and repeat. And again, we'll do that with ideal gases because multiple times through the loop is good. With water, look at this. We're starting at about 25, and the highest we're going to go is 80, right? So the highest we're going to go is 80. We're not going to get all the way to 80. So it's probably between 25 and 50 is where we're going to finish out, meaning the specific heat doesn't change in that range. So we're going to use C sub P of water to be 4.18 kilojoules per kilogram Kelvin. No, sorry, you can't see that. Right? We're going to use 4.18. We're going to assume that the average temperature is going to be somewhere between 25 and 50. We don't know T2 yet, therefore we don't know T average yet. But that's going to make a nice assumption. Now, for copper over here, for copper, I need sorry. You know what? We're just going to go to the next page. I messed that up. For copper, it's lecture 19. This is page 2 so far. Knowing that it's copper and roughly temperature C sub P for the copper. All right, so this is table A3A for liquids. I'm going to go to table A3B, which has solids, and then down here's table A3C has foods. But we don't have food, we have metal. We have metal as a solid. Okay, notice I've got copper at different temperatures. Oh, no, not Bing. Go away. I clicked on the search the web for this. I didn't mean to. Okay. Copper at these different temperatures. We're starting at 80 and we're going down to no more, like the lowest we can go is 25. The copper starts at 80. Copper starts at 80 and we're putting it in water at 25. So the final temperature is going to be somewhere between 80 and 25. So you see your specific heat there. It's 0.386 at 27 degrees C, and it's all the way at 0.393, all the way up at 100. We're somewhere in between those two. So basically what I'm going to do is I'm going to say this would be a good place where we would probably guess and check. And again, I'm going to guess and check with the ideal gas problem. We're going to go long on this video. That's okay. So we're not going to do it here. We're just going to say the specific heat of that copper is going to be around 0.39 kilojoules per kilogram Kelvin. And that's going to get us really close. Okay. All right, I'm going to stop sharing here. So to two significant figures, this is going to be correct. If I want a third significant figure, I'm going to have to do guess and check. Again, we'll do that with ideal gases, solids and liquids. I think we're just going to be fine with just two significant figures, and that'll be okay. Okay, so what do I know? T2 should be my only unknown now. I've got values, reasonable estimates for the specific heats. I've got a path to get this mass. I already know that mass. I know both T2s. Good to go. Okay. So if I solve for T2, if I solve this equation back here for T2. Yeah, come here. How you do your algebra to get to T2 here is fine with me. Just don't break any rules. MCU C sub P CU T2 plus MW C sub PW T2 is equal to MCU C sub PCU T1 plus M water C sub P water T1. This is T1 copper, T1 water. So what have I done? I've taken the negative, I've distributed the MC sub P's on both these terms here. I've taken the negative T1s, moved it to the other side of the equation, so it can now isolate T2 all on its own, right? Again, how you do your algebra to get to this conclusion is fine with me. Just don't break any algebra rules. MCU C sub PCU T1CU plus MW C sub PW T1W divided by the sum, because I've got to factor out both T2s have the same, or I've got two different things multiplied by T2. I've got to factor that out. Maybe that's the best way to say that. Math language is hard sometimes. So I'm going to divide by the quantity MCU C sub PCU plus MW C sub PW. And now this is my only unknown. Everything else here is known. Run numbers through. I'm going to pause and I'm going to let you pause, run these numbers, see what you get, see if you come up with what I get. Okay, you ready? I'm getting T2 here of about 300 kelvins. Right? 300 kelvins, which is about 27 degrees C. Does that make sense? Does that make sense? Well, let's look. I got 50 kilograms of copper, and you should have figured out you've got 120 roughly kilograms of water. So I have more water, much more water, and notice the specific heat. The water has more than 10 times the specific heat content of the copper. So I have more water with 10 times more thermal mass or thermal inertia. So the water is really not going to change much temperature at all. The water's going to heat up 2 degrees, and the copper's going to drop, what, more than 50 degrees? Yes, that makes sense because I've got more water, and the water has a much higher specific heat to change. So that makes sense. I mean, you never really, unless you really thought about it, and maybe it doesn't make sense. Hopefully kind of wrestle with that a little bit. That's one answer. What else? Are we done? No, the problem wanted to know what's the entropy change. All right. What's the entropy change? Well, here's the thing. The entropy change is going to be equal to the integral of dq over t plus sgen. All right? Well, there's no entropy, or I'm sorry, there's no heat transfer. There's no external heat transfer. All the energy transfer is occurring internally. So we're saying the whole thing, the whole big tank is our system, and the whole thing is insulated. There's no external heat transfer. So What I've got though, so I've got the entropy change is equal to the entropy generated. All right. That doesn't help us because this is not something I'm going to be able to solve for or calculate except for finding this. So I need to be able to find the change in entropy some other way. Well, entropy is a property. I've got to play by the rules for whatever substance I'm dealing with. What's my substance? Well, I've got some copper and I've got some water. So I have to play by the rules for both the copper and the water to figure out their entropy change. And then if I add those two together, that's going to tell me the entropy generated. Okay. Now these are capital S's. Remember, Gibbs equation said that for solids and liquids, Gibbs equation says that little delta S is about C sub P times the natural log of T2 over T1. That's little s. These are capital S's. What does that mean? That just means I need to use the mass. This is going to be mass of the copper times little s for the copper plus mass of the water times little s, little delta s for the water. And so since I've got solid copper staying a solid copper, and I've got liquid water staying a liquid copper, I can use this to find this for the copper and use this to find this for the water. And that's what I'm going to have you do. I want you to do that. I'm going to pause this. I'm going to go ahead and work out the intermediate steps, but I want you to pause it here and then get to a solution and see if you agree with me, okay? So I want to keep this video short, so I'm going to pause it here. All right, how'd you do? Well, here it comes. That's what I got. And it seems to match what is in the solutions that I've got in front of me. Why the negative sign? Steve, you said negative entropy is bad, right? Well, no, it's not necessarily bad. We just have to understand what it's telling us. The copper, what's happening to the copper? Notice the copper is going from a higher temperature to a lower temperature. What's happening to the molecules? Are they becoming more predictable or less predictable? Are they becoming more chaotic or less chaotic? Well, they're going from a higher temperature to a lower temperature. They're becoming less chaotic. Therefore, the copper is losing entropy. The molecules are becoming more predictable. They're becoming less chaotic. So we would expect a decrease in entropy for the copper molecules. We would expect an increase in entropy for the water molecules because they're going from a lower temperature to a higher temperature, and there's more of them, or there's more mass, I should say, and that mass takes much more energy in order to cause that temperature change. So we would see an increase in entropy, and the amount ends up being there's more entropy increase for the water than there is decrease for the copper, which just means it's a perfectly normal, irreversible process. We get positive entropy generation, which is what we expect. Again, negative entropy generation, we don't expect. Call Steve because something crazy has happened. All right, I'm going to stop this video here, and then we'll start an ideal gas problem.